Welcome back to the last section on rational equations in Chapter 8. After this, we'll take our test on this topic, and then we'll move into another topic for the remainder of the chapter. This section is specifically on solving rational equations, which you knew that it was coming. You knew we'd be solving these things before it was done. So, here we are. Let's take a look at our learning targets. And by learning targets, I mean learning target. The title of this section was Solving Rational Equations and Inequalities. The learning target, I can solve rational equations and inequalities. Brilliant. So, how to solve them? There are several ways that we can solve rational equations, and some ways will work for one thing, and some ways will work for another thing, and some ways will work for another thing. I don't like special cases. I'm going to show you the way that'll work for all of them. It'll generally be one of the easier ways, although sometimes you can do things a little bit easier, and we'll see that in a couple of them. And I'll point out some other things you could do, but I'm going to focus on one method that works for all of them. So let's start with the rational equation. Now, rational equations will have fractions with at least one variable in the denominator. So things that we could do here, we could write these using a common denominator, add them together, get it over common denominators, and then the numerators will be the same. Well, that works. That can be a pain. The way that we're going to do it, we're just going to get rid of the fractions entirely. And we're going to do that by multiplying by a common denominator. But before we do that, we need to figure out what our variable can't equal. I always want to say what x can't equal, but right now our variable is t. So what can't t equal? Well, that's nothing. Here t can't equal 0, and here t still can't equal 0, so t can't equal 0. All right, now let's multiply by the common denominator. Let's see, we need an 8 and a t and an 8t, so wouldn't it make sense the common denominator is actually just 8t? So let's multiply by that. When we do that, we have to distribute it to everything. Generally speaking, I wouldn't show this step right here. I would distribute and cancel just from here. But for this first one, I think it's probably important. So we have 8t, 1 times 8t, 2 times 8t, 17 times 8t, all over our denominators. Now let's cancel what we can. Here, the 8's cancel, leaving us with 1 times t, or just t. Over here, the t's cancel, leaving us with 2 times 8, which is 16. And over here, the whole 8t cancels, leaving us just with 17. So generally, I would go 8t, multiply 8 cancels, 1 times t. Here the t cancels, 2 times 8, and here they both cancel, it's just 17. And we'll see that as we go through some of these problems. But what I want to notice how all of the denominators are gone now. And so we're just left with t plus 16 equals 17. This is an easy one to solve. From here, subtract 16, t equals 1. Now we need to check it with what t can't equal. Is t allowed to equal 1? Yes, it is. So t equals 1. Let's look at another one. 7 equals 1 over w minus 4. We can multiply by the common denominator. But in this case, is there something we could do before that? Hey, we have a 7, we have a minus 4. Can't we combine these like terms? Add 4 over to the other side to get 11 equals 1 over w? Yeah, we could have multiplied by the w first. Would have had 7w and minus 4w, which would have equaled 11w. It would have still worked, but if you can combine like terms, go for it. Right? Before we multiply by that w, which is our common denominator, what can't w equal? Well, it's alone in the denominator. W can't equal 0. Now we can multiply by w. We'll have 11 times w equals, here the w's will cancel, and it'll just be 1. Well, 11w equals 1. Let's divide by 11. W equals 1 over 11th. Can w equal 1 over 11th? Yes, because that doesn't equal 0. It's close to 0, but doesn't equal 0. So w equals 1 over 11. Let's look at another one. We're just going to look through a few examples here because it's solving, it's computational. Here we have 1 over r minus 5 equals 7 over 2r. And we need to first figure out what r can't equal. Well, over here, r can't equal 5, because that's what would make it 0. And here, r can't equal 0, so r can't equal 5 or 0. Now multiply by the common denominator. We need an r minus 5, and we need a 2r. They've got nothing in common, so r minus 5 times 2r is the common denominator. If we distribute this, we have 1 times r minus 5 times 2r, and 7 times r minus 5 times 2r. We can cancel. R minus 5s cancel out, leaving us with 1 times 2r. Over here, the 2r cancels out, leaving us with 7 times r minus 5. So 1 times 2r is just 2r. And here we can distribute this to be 7r minus 35. Now it's a linear equation again. We can subtract the 7r to get negative 5r equals negative 35, and then divide by negative 5 to get r equals 7. Is r allowed to equal 7? Yes, because 7 is not 5 or 0. So r equals 7. So are we noticing that once we multiply by the common denominator, it becomes a really easy problem to deal with? Let's look at another one. 1 over x equals x over 6 minus 5 over 6. All right, what can't x equal? Well, x can't equal 0, and we don't care about this one. It's only in the denominator that we care. So x can't equal 0. Now what's our common denominator here? We have to have an x and a 6 and a 6, so 6x. We can multiply by that. When we distribute, the x will cancel here, leaving us with 6. And then over here in both of these, the 6's will cancel. We'll have x times x, which is x squared, minus 5 times x. And so we get 6 equals x squared minus 5x. Well, hey, that's a quadratic. We've worked with quadratics before. How are we going to end up solving a quadratic? Is that it? No. I'll give you a clue. It's the F word. No, not that one, the other one. Yes, factor. We're going to factor this. What do we have to do before we factor, though? The first step is we have to get everything equal to 0. So we're going to subtract the 6 over, and we get x squared minus 5x minus 6 equals 0. Now we can factor this side. We're going to have our two sets of parentheses. What times what equals negative 6, but adds to give us negative 5. See, 2 and 3 will add to give us the 5, but they have to be different signs to give us the negative 6. How about negative 6 and 1? And so we have 0 equals x minus 6 times x plus 1. X minus 6, that'll give us x equals 6. And then here we have x equals negative 1. So x equals 6 or negative 1. Is x allowed to equal 6? X allowed to equal negative 1? Yep, neither of those is 0. So x equals 6 or negative 1. If we plug those back in, we have 1 over 6 equals 6 over 6. That's 1 minus 5 over 6. This would be 1 over 6. If you plug in negative 1, we get negative 1. We have negative 1, 6 minus 5, 6 is negative 6, 6, which is negative 1. So both of those do work if we plug them back in. All right, another one. This one's fairly similar. M plus 12 over m equals 7. This is barely a rational function. We only have that one denominator there. It just happens to be a variable. So, first step, what can't m equal? Well, m can't equal 0. Now we can multiply by the common denominator. There is only one denominator, so multiply by m. We're going to get m squared plus the m's cancel, so we have 12 equals 7m. It's a quadratic again, so let's get it equal to 0. So subtract the 7m over, then factor. What times what will equal 12? That'll add to equal negative 7. Negative 3 and negative 4. And so here m could equal 3 or 4. And neither of those is 0, so m equals 3 or 4 is our solution. Another one. So I told lots of examples today, but hopefully they should be getting kind of easier, and each one's a little different. Here we have negative 2x over x plus 2 plus x over 3 equals 4 over x plus 2. So, first thing, what can't x equal? Well, x can't equal negative 2. That's nothing. And x can't equal negative 2, so x can't equal negative 2. Now, to multiply by the common denominator, we need an x plus 2, and we need a 3, and we need an x plus 2. Well, we already have an x plus 2. So we just need an x plus 2 and a 3. So 3 times x plus 2. When we distribute, here, the x plus 2 will cancel. So we have 3 times negative 2x. That'll be negative 6x. This one, the 3's will cancel. Then we can distribute. X times x is x squared plus 2x. And then here, the x plus 2's will cancel, leaving us with 3 times 4 is 12. So we get negative 6x plus x squared plus 2x from that distribution equals 12. It's quadratic again, so we can move the 12 over, combine our like terms to get x squared minus 4x minus 12 equals 0, and then factor. What times what equals negative 12? That adds to give us negative 4. Negative 6 and 2. So x minus 6, x plus 2 equals 0. So x could equal 6, or x equals negative 2. Can x equal 6? Yeah. Can x equal negative 2? No, x can't equal negative 2, so that one doesn't work. So it's just x equals 6. There's only one answer. That's okay. Let's take a look at another one. Here we have in our denominator x minus 3 and 2 and 2x minus 6. Well, 2x minus 6 can factor, so let's do that first. We can pull a 2 out of both of them to get 2 times x minus 3. Now, what can't x equal? Well, x can't equal 3, so x can't equal 3. In our common denominator, we need an x minus 3, and we need a 2, and this one's already x minus 3 and 2, so just 2 times x minus 3. When we distribute, here, the x minus 3 will cancel, leaving us with 2 times x. Here, the 2 will cancel, leaving us with x times x minus 3, which would be x squared minus 3x. And here they'll both cancel, so we just have the 6x left over. So we had the 2x, x squared minus 3x, and 6x. Again, quadratic. Let's subtract the 6x over and combine our like terms. 2 minus 3 is negative 1 minus 6 is negative 7x. There's the x squared. Then to factor, we only have 2 terms. What's the first step in factoring after we get it equal to 0? Pull out what they have in common. They both have an x. So we pull out an x. We have x times x minus 7. Well, so either x could equal 0 or x could equal 7. Neither of those is negative 3, and so we get 0 or 7. And then last one for this stuff. 3x over x plus 1 equals 2x minus 1 over x plus 1. So first step, what can't x equal? Well, x can't equal negative 1. And then in this case, we could multiply by the common denominator, which is x plus 1. But doesn't it make sense if we have something over our denominator equals something else over the denominator? These two things have to be equal, right? If we had 5 over 7 equals x over 7, wouldn't 5 have to equal x? It's the same basic principle here. So we have our common denominator. So 3x has to equal 2 minus x, or 2x minus 1. Subtract the 2x over. X equals negative 1, but x can't equal negative 1, so that doesn't work. We don't have any other options here, so it's just no solution, which is a possibility. It's possible that it will never equal. So this is solving rational equations. Again, basic steps: figure out what the variable can't equal, multiply by the common denominator to get rid of the fractions, and then you'll either be dealing with a linear equation or perhaps a quadratic equation. You won't be dealing with much more than that. Solve it to get down to your solution, and then make sure you check to make sure that your solution actually will work. And that's all that this is part of. Like this w does not equal 0, x does not equal -2. That's not part of the answer. It's just to possibly cancel out part of the answer. All right, so that's rational equations. For rational inequalities, it's basically the same thing. We're going to start out with an inequality. X plus 3 over 2x is less than 2. And then we're going to pretend that they're equal. So we need to figure out what x can't equal. Here, x can't equal 0. And then multiply by the common denominator, 2x. So that'll cancel out over here, so we'll have x plus 3. Then 2 times 2x is 4x. Subtract the x over, so we have 3 equals 3x, divide by 3, x equals 1. And so from here, because we have an inequality, we're going to be dealing with a range of values, not just one value. It's not just x equals 1. That's where it's equal to 2. And so we're going to make a number line. And we're going to put some values on it. We're going to put our solutions, and we're going to put where x can't equal 0. These would be vertical asymptotes, by the way, if we were graphing them. And so we'll put 0 and 1 on. It is important that these go in the right order. And that gives us regions. We could be less than 0, we could be in between 0 and 1, and we could be bigger than 1. It'll work for some of these regions. Probably either the two outside or the middle one, but not necessarily, so it's important to check them all. We're going to plug in a number that's in this region. I'm going to pick -3. And we're just going to plug it into the inequality and see if it works. Now, I picked -3 because -3 plus 3 equals 0, and 0 over -6 equals 0, and we can see that 0 is less than 2. As long as we pick anything less than 0, it will make this statement true. And so that one works. Out of all the shapes and stuff that I have in this, a check mark is not one of them, so we get smiley faces. How fun is that? All right, now let's pick a number in between 0 and 1, 0.5. So plug it in. We have 0.5 plus 3 over 2 times 0.5. 0.5 plus 3 is 3.5. 2 times 0.5 is 1. So we have 3.5 is less than 2. That does not work because 3.5 is not less than 2. And then let's plug in a number bigger than 1, 3. Could have picked 2, but the nice thing about 3 is that we get 3 plus 3 is 6 over 2 times 3, also 6, and 6 over 6 is 1, and I know that 1 is less than 2. So that one works as well. And so now that we know where it works when we're less than 0, so x is less than 0, or it works when x is greater than 1. So x is less than 0 or x is greater than 1. I'm missing my answer. It's x is less than 0 or x is greater than 1. The program crashed and I had to fix it, and I thought that I got everything. Apparently I missed something. Anyway, if we wanted to look at a graph and see what was happening, which is another good method of looking at this, here's our graph. We have the x plus 3 over 2x is the red one, and 2 is the blue one. We want to know when is the red one less than the blue one. It's less over here, which is from -infinity up until 0, which is that vertical asymptote. And then it's bigger from the vertical asymptote to 1, and then it's less again from 1 to infinity. So again, we can see that it works when x is less than 0 and x is greater than 1. And so that's solving rational inequalities. It's basically the same. We're going to use a number line to plug in some values. You can look at your graph to get some more sense out of it. But the solution part is the same. Anyway, that's solving rational equations and inequalities. Again, check to see where a variable can't equal. Multiply by a common denominator, solve, and then double check that domain restriction. And that's it. Anyway, I hope you had a great time. Make sure you post a comment, and I will see you in class.